Hi there, this is Coach Eikrem, and welcome to our unit on moles. And moles, I love this unit because not only is it very sensible, it's math-based, so it makes a lot of sense and it's very logical. It's also a super wonderful excuse to have pictures of very cute moles on every single slide. So get ready for that. See, so cute. All right, here we go. In any reaction that we're performing, there are huge numbers of particles that are reacting. So we need a way to count these particles in the same way that when you go to the grocery store, you don't just buy one egg. You buy a dozen eggs. And you know that to be 12 eggs. That's kind of common knowledge. So in chemistry, common knowledge for us is a mole of something. And it provides us a way to take a huge number of something very, very small and put it into large groups that we can manage. And 1 mole is the equivalent of 6.02 times 10 to the 23rd particles. And we can also read particles as atoms, or molecules, or formula units. So 1 mole of something can be 6.02 times 10 to the 23rd molecules. 1 mole can be 6.02 times 10 to the 23rd atoms, or formula units. We abbreviate moles as MOL. Please don't ever abbreviate it as M, because that means meters, or ML, because that means milliliters. So it's MOL. So let's do a practice problem. How many atoms of gold are in 2.5 moles of gold? So this is where I'm starting, this is where I'm going. So we've got 2.5 moles of gold. That's my given. And we learned from the previous slide that moles to anything else, particles, you can even have moles of pencils for all you know. You wouldn't, that would be a huge number of pencils. But in this case, 1 mole is going to be the equivalent of 6.02 times 10 to the 23rd atoms of gold. Cross off our units, and when we work it out, we get 1.505 times 10 to the 24th. Now you remember, everything comes back to haunt you from the beginning of the year, and significant figures is one of those things. This is still important, and you still need to use them. So we've got 2 significant figures in our given. Therefore, this has to be rounded to 2 significant figures, so your correct answer is going to be 1.5 times 10 to the 24th atoms of gold. And make sure you box your answer, especially on these problems, otherwise your work's going to get very messy very quickly. Oop, I might have gone too many slides. Let me just check. Nope, we're good. Okay. How many formula units of sodium chloride are in 0.25 moles of sodium chloride? So using what we know, we've got 0.25 moles of sodium chloride. We convert it from formula units to moles. 1 mole is going to be the equivalent of 6.02 times 10 to the 23rd formula units of NaCl. Cross off your units. And once you solve that out, you get, and go to the correct number of significant figures, which in this case is 2. It's going to be 1.5 times 10 to the 23rd formula units of NaCl. There we go. How many moles of water are in 3.01 times 10 to the 23rd molecules of water? So this time you're starting with molecules and you're going to be converting back to moles, but the process is still the same. Remember, you don't have to have, some people think that, you know, one needs to be on top of the other in your dimensional analysis, but that's not true. These are interchangeable because they're ratios. So we've got our given, which is 3.01 times 10 to the 23rd. I'm going to do this, molecules of water. And we know that 6.02 times 10 to the 23rd molecules of water is the equivalent of 1 mole of water. Cross off our unit, and when we work it out and go to the correct number of significant figures, we get 0.500 moles of water. And make sure to box your answer. So when we're using mole particle conversions, the terminology, you need to make sure you have the terminology correct. So for example, when we're reading a chemical reaction like this, you could read this as 2 molecules of hydrogen gas react with 1 molecule of oxygen gas to produce 2 molecules of water. And this molecule is the same, so if you have 1 mole of it, it would be 6.02 times 10 to the 23rd molecules. And your term for particles can also be atoms or molecules. And remember, when you're talking about an atom, it has to be the individual particles of an element. When you're talking about a molecule, you have to be talking about the individual particles of a molecular compound, which must, remember, contain nonmetals and metalloids, or a diatomic element. And just to refresh your memory, the diatomics are these halogens right here, plus oxygen, plus nitrogen, plus hydrogen. And that's the terminology you would use for those. And you can remember the diatomics via I bring clay for our new hut. So make sure that when you're doing this, you're using the right terminology. If you're going from moles to atoms, you're using that correctly. You're not going from, you wouldn't, use molecules in place of atoms. You have to make sure you're using the correct terminology when you do your conversions. So how did scientists come up with this number, 6.02 times 10 to the 23rd, and why do they use this particular number? The way they got it was by looking at carbon. And carbon has an average atomic mass of 12.01 AMUs, meaning that if you have 1 atom of it, it's going to have a mass of 12.01 AMUs. But they wanted to be able to use convenient atomic masses for the elements, but on a larger scale. And so they kept the numbers the same, but they changed the unit. So now they said, we've got 12.01 grams of carbon. Same number, just a different unit. We're going to use grams now instead of AMUs. So they know that 1 atom of carbon is equal to 12.01 AMUs, but how many atoms of carbon are in 12.01 grams? So if I basically, came into the lab and I put 12.01 grams of carbon on a scale, they wanted to know how many atoms of carbon are in there exactly. And they experimentally determined that it's 6.02 times 10 to the 23rd atoms. And this number now we call Avogadros number. And it actually now applies to any element. If you look on the periodic table and you look at the atomic mass, so for example, let's look at, hydrogen, 1.008. Okay? If you take in your lab on a scale 1.008 grams of hydrogen, then, according to Avogadros number, you've got 6.02 times 10 to the 23rd atoms of it. That's how many atoms of hydrogen you have. And now that we know what we know with conversion factors, that also means that you'd have 1 mole of hydrogen. So in our next video, we're going to talk about how do we use that number to convert now between grams of an element to moles of an element using what we call molar mass.